probability of scattering that way or that way or that way or that way for the same angular theta. The theta is defined as, like, here's your x-axis, and if you scatter by this angle theta, right, or the same angle theta, so you got a kind of circle here that generates a cone. So here's here where my finger is. Let that be the target center, and then angle theta. So you can imagine, you can draw us a kind of cone. Imagine like an ice cream cone, and the angle theta is the angle between the x-axis, the incoming axis of the incoming beam, this way, and then it scatters through an angle theta. Right? So you can draw a sort of cone with the same angle theta. So you get that kind of symmetry. So whether it's that way or that way, the scattering probability is equal. So you have that, and we'll talk about that in the next session a little. All right. So the scattering probability will depend on the distance r between the scattering center and the particle. Okay, and this technique was used, for example, famous experiment in 1911 by Rutherford. Rutherford discovered the nucleus. I mean, major discovery, one of the big ones of the 20th century. By using this technique of scattering, he shot in alpha particles, which are just helium nuclei, the helium atoms without the electrons. So he shot in helium nuclei to gold. I mean, the target was gold atoms, a very, very thin foil, gold foil, and was deeply surprised when some of his alpha particles shot right back, as though they were hit, as though the target they hit was extremely heavy, and hence he realized that the core of an atom must be very heavy and very dense, hence he called it the nucleus. So that major discovery was found by using scattering techniques. Right? Now, when we get to the math, we will use something called partial wave analysis. And you may ask, well, why partial? I mean, what is partial about it? Why isn't it full? And that I won't explain it at the moment, because we need to understand that. You need to understand a few more concepts, particularly cross-section. So just put that off for the moment. Just be aware that an important concept for this chapter is partial wave analysis, and using this technique, we can describe pretty well the whole of scattering theory. So bit by bit, this concept of the partial wave will become clearer. But I can't give it to you at the moment because we need a few more steps, a few more stepping stones. All right. So we need to describe, in a sense, how much flux, in a sense, is coming in. We need a measure of how much flux, how many particles. Well, here it is here. So the incoming, the targets, the particles that are coming in. Those particles' current density is measured in units of the number of particles per unit area, so square meter. So the number of particles per square meter per second. Okay, that's a measure of of the intensity, if you like, of how many particles per unit area per second. That's we'll call that J after a while. This degree of the current density or flux related, right? Now, after the scattering, so imagine a particle beam. So a particle comes here, gets scattered by this scattering center, by the target, and then gets deflected and hit. Well, imagine it gets deflected in the plane of this whiteboard. Imagine, but I mean, it could be any direction. Could be any direction at all. So but imagine it does get deflected in the plane of the board, then the deflection angle would be, by what angle did it deflect relative to the, its incoming direction. It's the x-axis going this way. And say it deflects up that way. So this angle here, this angle, would be theta. Okay. Now, the distance r, the shortest distance between the target and the approaching particle, if that r is large, then you would expect very little deflection, right? So your theta then will be depend on the r. So if you have a large r, the deflection angle, if you're right, you expect it to be pretty well zero, right? But if that distance r, the distance between the scattering center and the particle, if that distance is small, then you expect to get quite hefty scattering. And that was certainly the result with Rutherford's famous experiment. Right? When r was very small, your alpha particles got bounced right back. Okay? All right. Now, before one of the stepping stones for partial wave analysis is something called the cross section. So and to explain this, I need to explain other things. It's going to be a logical chain. I need to explain A before I can explain B, and I need to explain D, I need to explain C. To explain C, I need to explain B, and to explain B, I need to explain A, and so on. There's a whole chain of such concepts. But we'll get there eventually. All right. Okay, so now starting to explain by what's meant by the scattering cross section, and you'll see eventually why this concept is called a cross section, because in a manner of speaking, we slice a 3D object, and what results, this sort of surface, has relevance to this concept. Since I've run out the end of the session, we imagine we have a flux of J particles per square meter per second. Right? So we start with an incoming beam that has an intensity, if you like, of J. So J just simply means J is the number of particles per square meter per second coming in, approaching the scattering center or the target. Right? And after the scattering, these particles, they can scatter in all directions, right? I mean, imagine a sphere of unit dimension, so a radius 1 sphere centered with the scattering center, the target, at the center of the sphere. Okay? So the incoming particle could scatter in any direction. So it could hit, in a sense, it could hit that unit sphere at radius 1 anywhere on the sphere. Okay, so that's what's meant by it can scatter in all possible directions. Right? I'll take that up at the next session.